Welcome to NPTEL online course on fractals and multifractals. In the previous lectures, we have discussed the box counting dimension, topological dimension and Hausdorff dimension of an object. So, especially in the last lectures, we have discussed the Hausdorff dimension of an given set in R power n. We saw some example in which there are attractors are generated by the different iterated function system, whereas they have the same fractal dimension. Now we are in the situation that we need to distinguish these two fractal by some other alternative measures. So this scenario will be resolved by the multifractal measures. So in this lecture we are going to discuss the construction and the definition of multifractal measures. So let me start this lecture by recalling the Hausdorff dimension. Suppose K is a subset of R power n and S is a non-negative number, that H delta of K for any delta greater than K is defined by the here, where delta tends to 0, then this quantity Hs of S K is called the S dimensional Hausdorff measure of K. Here Ui is a delta cover of K, so each of Ui has the diameter at most delta. So this S is always existing for any subset of K of R power n, neither it is infinity or 0. Now there is a critical point S where this measure jump from the infinity to 0. That critical point we can call it as the Hausdorff dimension, that we are formally defined here. Here formally we define the Hausdorff dimension as where the S dimensional Hausdorff measure jump from the infinity to 0. That critical point we can call it the Hausdorff dimension. This is the definition of Hausdorff dimension, and we obtained the Hausdorff dimensions of the sets given in K, the different method we discussed. Now here we are taking the cover of K by considering this arbitrary set Ui have the diameter at most delta. Now instead of taking the cover at most delta, we are going to take the diameter exactly at delta. That leads to give the definition of box counting dimension. Let S be any set and n of delta means minimum number of boxes required to cover S, the set S. Then it will follow the Power relation n of delta directionally proportional to the delta power minus d. Here by taking the logarithm one can find the box counting dimension of the set S. We can denote it as dB or simply the d. Limit delta tends to 0, logarithm of n of delta over log of size of the boxes 1 by delta. This dimension we can call it as the fractal dimension. Now you can consider the curve like this one, the object like this one. In both the method, consider these are both are same object. In the Hausdorff dimension, in the DH method and DB method, this is finding the Hausdorff dimension of the object. This DB denote the procedure for finding the box counting dimension. In both the method, we are covering the object by the sets, closed sets or spheres or anything we are covering, but means usually we are giving the a numerical value to the set. That means we are measuring how big is the size. This is our motive. The how big is the size. For that, the given set is decomposed into the small pieces. Then for finding the size of the set, we are finding the sizes of the pieces, then take their sum, then the sum will give the measure of the or size of the whole object. Now here there are two type of the decomposition. We are decompose or separate or partition the set into, there are two types. Here we are separating this set by this type of covering, like this type of covering. We are cover this one by like this one, the set is covered. You can observe that each set has the different size. Now here we are covering this set by the equal sizes of boxes, equal size. Each box has the equal size. In the Hausdorff dimension, we are taking the cover by utmost delta cover. Here we are taking the exactly delta cover. Each of box which has the size exactly delta. Here the each of box has utmost delta. Then we are using the power law relation and obtaining the Hausdorff dimension as well as the box counting dimension. Then we are assigning some number to the set and we are saying that number gives the box counting dimension for the given set, and we are saying that set gives the, that number gives the Hausdorff dimension for the given set S. Now you can consider this scenario. There are 3%. I have 6 coins. For each person I am giving the two coins. Can you say I equally distributed this coin to all the 3%? For first person 2 coin, the second person 2 coin, and third person 2 coins. Like that I distributed 6 coins all the 3%. Can you say this, the distribution is equally distributed? No way, because here I never mention about what is the denomination of my coins. Suppose I have 2 1 rupee coin, 2 2 rupees coin, and 2 5 rupees coin. The first person I can give 1 1 rupee and 1 2 rupees, and second person again 1 1 rupee 1 2 rupees coin, whereas in the third person I gave 2 5 rupees coin. So now I have given 2 coin for the all the person. If you consider the number of coins, it is equal for all the 3%, whereas if you are considering the denominator, it is not equal. So here in the box counting dimension and the Hausdorff dimension, both the numbers are assigned for the set by counting the number of boxes, counting the number of whereas it is a different size or equal size, no matters. It just assigning the number by counting the number of boxes. So what actually missing? What is the inside information in each of the boxes? What is inside these boxes? It is actually missing in the box counting dimension as well as in the Hausdorff dimension. So this number, the box counting assigning one number to the set, given set, and also the Hausdorff dimension assigning one number to the set. But this number does not give the distribution of the set inside the boxes. How the set is distributed over this region is not clearly mentioned. Also the set is how behave inside the box, and the local property also not properly mentioned. We know that the fractals, in fractals, if you are changing the scaling, the pattern is never changed. It's similar to the, it's with respect to the any scaling, the pattern is similar. In all the corner, the pattern is similar. That means if you are taking the small part of an object, it reflects the whole. So when you consider the small part, then it reflects the whole. Whenever you are reducing the sizes, the pattern is never changes. It looks like the similar, almost the same. But here, if you are consider these boxes are just counting to cover the sets. What is inside the box, it is actually missing from the both the dimension. Now in the multifractal measure, it will consider how the object is distributed over this region in each inside the box, how it is distributed in the each of boxes, it will assign the measure. Then based on that, the multifractal measure will be calculated. So the multifractal measure is the more appropriate measure to classify the fractals compared with the box counting and the Hausdorff dimension. However, if you are choosing the particular parameter of multifractal measure, one can obtain the box counting values or Hausdorff dimension values. That will discuss one by one. Let me start with this lecture by giving some preliminary mathematical tool which we need to create the multifractal measure. So that first one, we start with the Legendre transformations. I quickly recall what is the Legendre transformation. So to understand the significance of f of alpha, we need to use the Legendre transformation on f of alpha, where this f of alpha I consider as, suppose I have the structure like this one, then I cover this one by boxes, doesn't matter whether it is equal size or different sizes. Maybe I, without loss of I am considering all are equal sizes. For all the boxes, I am assigning some measure mu. The measure of the boxes I am calling as mu. All the boxes has the size of the boxes is, I am calling as, it is alpha. Inside the box, one can understand the size of the boxes is alpha, then mu is defined as, maybe I can call the density of the boxes. So obviously with respect to this alpha, all the boxes is not containing the same measure. It depends on the set. If you are considering the more irregular object like this one, this is regular, then here like this one, then this box containing more density point, whereas this box containing the less density point. So the mu of box will vary with respect to the different alpha. Then I am calling this is f of alpha is ln of mu of alpha by, I am defining this exponent as the number of boxes having the measure mu. I can call it as ln of mu of box by ln of alpha. I can call it as f of alpha, that I will define properly in later things. That is, I can call it as f of alpha here. So we need to apply the Legendre transformation on this f of alpha. So before we apply this, we first understand the principle of Legendre transformation. For this, we consider the function y equal to y of x1, x2, xn in r power n. Legendre transform can be described as a method whereby the derivative mk, that means the partial derivative of each variable, can be denoted as mk equal to dou y by dou xk, can be considered as an independent variable without sacrificing any of the mathematical content of the equation 1. So, this here x1, x2, xn's are independent variable. Now, we are going to transform y with respect to the derivative of their dependent variables, dy by dxk, partial derivative of dependent variables. Now, for the sake of simplicity, let us first consider a function of a single variable. For instance, y equal to y of x. Now, m equal to dy by dx. This m is the slope of this curve y of x at the point x comma y. The curve y of x at the point x comma y. In order to treat m as a independent variable in place of x, one may attempt to eliminate x between the equation 2 and 3, thereby getting a y as a function of m. By these two equations, one can eliminate x, therefore y can be expressed as in terms of y. However, this is not a correct, since in doing so one would sacrifice some of the mathematical content of 2, in the sense that knowing y as a function of m, we will not be able to reconstruct the function y equal to yx as emphasized. So, for example, consider the function y equal to e power 2x by 2. The m equal to slope dy by dx, which is equal to e power 2x. Hence, y of m we can write m by 2. From these two equations we eliminate x, therefore y of m we can get as m by 2. Let us try to reconstruct y of x for the relation ym equal to m by 2. Since m equal to dy by dx, which is equal to 2y, dy by dx, which is equal to 2y, we get, just you can multiply, cross multiply here, you will get 2 times y. So, 2 times m can be read 2 times y. So, then y of x, by integrating this one, then y of x one can get c times e power 2x. So, where the integral constant c remains unspecified. So, the c is unspecified. So, clearly the inadequacy of this procedure arises from the fact that the relation y equal to ym involves dy by dx, and the integration required to get yx from this differential equations yields y of x up to an unspecified constant of integration. Also, it is straightforward to realize even from this simple example that a curve, a sequence of points y equal to y of x can also be represented uniquely by the relation c equal to c of m that describe the tangent lines. In other words, a knowledge of the intercept c of the tangent line as a function of the slope m enable one to construct the family of tangent lines and thence the curve. See, consider this curve. Consider the function, this function f of x, y equal to f of x. By taking the derivative means derivative at the point x, we need to draw the slope at this point, the point x naught comma f of x naught, this point, draw the tangent line. The derivative provides the slope of the tangent line at the point P. So, this is m, this is 1. So, slope equal to m, that means f dash of x naught provide the slope of this tangent line. So, the given function y can be represented with respect to the tangent line at the point P, which can be y minus f of x naught equal to m times x minus x naught, or y equal to mx plus c. By the tangent line, it can be represented by this form from here, whereas this tangent line, instead of this considering this point P, this tangent line will intersect the y-axis at the point c comma 0. So c can be written as f of x naught minus m times x naught. So it has the alternative form y minus f of x naught equal to m times x minus x naught. So this y we can write in the two form with respect to the slope and slope of the tangent line, and another one the tangent line intersect the y axis at the point here C, at the point 0 comma C, this point. So there are two different representations. Now we are going to use this one. Now the question is how to calculate C of m if we are given y of x. If we are given y of x, how to calculate the C of m? The appropriate mathematical tool is known as the Legendre transformation. So consider the tangent line that passes through the point x and has the slope m and intersect point C on the y axis, then C in the form of y minus mx can be taken as the analytical definition of C. In fact, C is the Legendre transform of y. Now let us discuss the Legendre transform in general of a function y which depends on the variable x1, x2 up to xn. In the nth tuple we will move for the general case. Consider the function y equal to y of x1, x2, xn, then n number of dependent and independent variable. The partial derivative of y with respect to its variables are, it is denoted as ai. So a1 denotes the dou y by dou x1. Like that a2 denote the partial derivative of y with respect to the second variable. Now consider ai equal to dou y by dou xi, where xi j not are equal, j not equal to I. Now x1 is replaced by a1, that means dou y by dou x1 as independent variable. We can then define a new function as phi equal to y minus a1 x1. In general, phi can be written as y minus sum of ai xi, where sum running over 1 to n, running over 1 to n. The new transformed state function phi is now a function of ai, function of ai. Such a transformation from the original variable xi to a new state variable is called the Legendre transformation. We are written phi in term of ai. In other words, the Legendre transforms replaces the point based representation y comma xi of a curve with the tangent based representation. Point based representation is converted to the tangent based representation using slope intercept form, while preserving all the information about the original curve. The no information is losing from the original functions. So this procedure one can convert y in term of x with respect to x is given, one can write y in term of its tangent based representations. Once we know the fundamental principle behind the Legendre transformation, we can follow the simple working procedure described below without having to go through all the detail. We first have to find the differential dy of the function y, whose Legendre transform we intend to find. If we find the Legendre transform of y, take the differential of y, it is denoted as dy. That means dy equal to dy by dx times dx, which is equal to a dx. We then rewrite it as dy can be written as a dx plus x times dA minus x times dA, the product rule. Hence we can write dy as dy equals differential of ax minus x times dA. Then dy minus this term comes to this left side, minus d times ax equal to minus x times dA. Then take the differential here, that means the product rule again, differential of y minus ax equal to minus x times dA. Now the quantity in the parenthesis of the left hand side, the quantity in the parenthesis left hand this side of the above equation can be defined as a new quantity, that means phi, that equivalently written as y minus ax. This is y minus new quantity, y minus ax is defined as phi, which according to the right hand side of equation 4 reveals that it is a function of a, which is in fact the slope of the original function. So likewise we can find the Legendre transform of given function. So the sketch is given here. So consider the function, or consider function of n independent variable, take the partial derivative of each variable and denoted it as mk. Now independent variable in place of x, without losing any information we need to transform y. For one variable case, y equal to yx, m equal to dy by dx is the slope of the curve yx at the point x comma y. M is the slope of the tangent line drawn at this point. For example, if y equal to y of m is not enough, for example, consider y equal to e power 2x by 2, the derivative is 2x, ym is m by 2. To reconstruct y of x, make this relation ym can be written as m by 2. So m is dy by dx equal to 2y. So y of x, if you integrate, then one can get c e power 2x, where the integration constant is unspecified, we are unknown, remains unknown. So knowing y as a function of m involve dy by dx. Knowing the y as a function of m involve dy by dx. Integration gives y of x only up to a constant. So a curve can be represented uniquely by the intersection of its tangent line. We are using this idea. So at the point x comma y, the tangent line has the slope m and intersect point c on the y axis. Hence c can be written as y minus mx. Thus c equal to ym describe the family of tangent lines and hence the curve. This is the slope of the tangent line m1 intersects this x1 in the x2 intersection point here. Likewise the x3 intersection point here, it is m2 here, m3, we will get the tangent line intersection point. So family of tangent lines y equal to mx plus cm, where different intersection point for the different point. The curve is the envelope of this family of line. Now the general definition, if you have the n independent variable up to n independent variable, so here it is xi, where xi, this is I belongs to 1 to n, then ai denote the partial derivative of each y with respect to the variable xi. Replace x1 by a1 as independent variable, define phi equal to y minus a1 x1. In general, phi equal to y minus sum as ai xi. The new function phi is now a function of ai. This transformation from the variable xi to the variable ai is called the, we are transforming y in form of writing xi, we are writing as the ai. This transformation we are calling as the Legendre transformation. The working procedure for the one variable, find the differentiation of y, then write dy as a dy by dx times dx, then it can be a dx. Rewrite this one under this form, then this can be written this form finally. So that define the Legendre transform, phi can be equivalent to y minus ax. From d phi minus x dA, we see that phi is a function of a, since the differentiable involves only dA. Hence a equal to dy by dx is the slope of the original function y. Thus, the Legendre transform represents the curve by the collection of its tangent line through slope m and intersection point c, not by the collection of the point x comma y, not the point of x comma y. Now, let us go to for the theory of multifractality and how to the Legendre transform is applied on the theory of multifractality. So, in general, one can describe a set. Now, I need to find the multifractal measure for the set S. Describe a set of points describing an object which can be divided into boxes labeled by an index I, such that ith boxes will have ni number of points of the total n points of the set. That means S is divided into n boxes such that each boxes we are counting the number of points. So, here we are counting the number of points for each boxes instead of simply covering the boxes. So, I have the set S, then I can divide this set into boxes such that each box for index I such that the ith box will have ni number of points from the total number of points n. These points are sample points describing the content of the underlying measure. Now, let us use the mass or probability mu I defined as ni by n. That means the density, mass or probability of the ith box is defined as mu I equal to ni by n. Is the ith cell to construct weighted D measure which we write md of q comma delta is written as sum of I equal to 1 to n mu I power q delta power d. That means this quantity I can take as z of q comma delta power d, because size of the boxes it depends and mu I depends on this power. If by varying different power we will get the different mu I, and also it depends on the size of the boxes. We are dividing the boxes of size delta, and mu I is defined as number of points in the ith boxes divided by total number of points in the boxes, overall the boxes. Then this measure depends on q and delta, therefore I am writing q comma delta times delta power d. The mass exponents tau q for the set depends on the moments. I can write z q comma delta equal to mu I power q of order q chosen, and this is chosen as like this one, qi power q. It is also known as the partition function as it behaves in a similar manner when one tried to find an analog of multifractal formalism with thermodynamic phase transition. So, here tau q is like defined as this moment. The mass exponent tau q for the set depends on the moment is given in 5 for the order q. Like n of delta of bare d measure the partition function, if we may call z q comma delta also often exhibit Favor law distribution. This exhibit the Favor law distribution z of q comma delta is directly proportional to delta power minus tau q. By applying the logarithm on here, ln of z q comma delta equal to minus tau q times ln of delta. So, tau q can be obtained as ln of partition function psi of q comma delta over ln of 1 by delta. This minus goes to power, it becomes the 1 by delta. the mass exponent, where the exponent tau q is called the mass exponent, not the fractal dimension. Because while obtaining the fractal dimension, we are obtaining number of boxes is required to cover the object A is denoted as n of delta, that means minimum number of boxes, it is equal to minus d. This d is the fractal dimension, but here the tau q is not a fractal dimension, it is a mass exponent. If it is non-linear in q, it is non-linear in q. That means with various q we are getting the various measure, these are various density. The mass exponent is more revealing the simple fractal dimension, as we shall soon find out. It can equivalently can be defined as like this one. The mass exponent is now defined as like this one. By using the power law property, one can obtain this one. Then equation 5 and 6, in the 6 you can replace in 5. Z of q comma delta, here one can write, then mdq, that means the d measure of set S with the q and delta can be written as delta power d minus tau q. So this delta tends to 0, limit delta tends to 0, there is a critical point, the tau q, where d is greater than tau q, it is 0, like the same argument in the Hausdorff dimension, where this d is less than this tau q, it goes to infinity. There is a jump from infinity to 0, there is a point tau q. The weighted d measure has a critical mass exponent d, that means d we are doing as tau q, for which the measure neither vanishes nor diverges. As delta goes to infinity, there is a critical point tau q. Now the weighted measure is characterized by a whole sequence of tau q. This weighted measure is characterized by the tau q, it moments that control how the movement of the probability mu I scale with delta, because that mu I q we are defining. So based on this measure mu I, the based on the measure, how the exponent tau q that control how the movements of the probabilities mu I scale. If we are considering this as probability, we are taking the probability power q is the movement. This depends on the size of the boxes of delta. Now what are the properties of the mass exponents tau q? First you can denote, we first note that if we choose q as 0, then we have mu I power q, it is 0 equal to 1, and hence we find z of 0 comma delta is n of delta. This number z of 0 comma delta equal to n of delta is simply the number of boxes needed to cover the support, and therefore tau of 0 equal to d is the Hausdorff viscous dimension of the support and tells nothing about the content inside the boxes. It is simply count the number of boxes. This becomes 1, mu I becomes 1 here, mu I becomes 1 here, it simply count the number of boxes. So nothing says about what is the content available inside the boxes. Now if you are taking all the boxes are equal sizes, then it is equal to the fractal dimension, because if you are using the arbitrary boxes of diameter less than delta, then this will equal to the Hausdorff viscous dimension. If you are taking the equal boxes, then it will coincide with the fractal dimension, that means the box counting dimension. On the other hand, the probability are normalized, that means sum of mu I equal to 1, and it follows from the equation 7, from this equation 7, if you are taking q as 1, mu I equal to 1, and it follows that from equation that tau of 1 equal to 0. If you are putting tau of 1, we are getting as 0. Choosing large value of q, say 10 or 100 in equation here, equation 1, in the equation 7, favor contribution from cells with relatively high value of mu I, since mu I power q is relatively greater than mu I power q, with mu I is greater than mu j if q is greater than 1. Q is greater than 1. Conversely, if q is less than or equal, relatively less than or equal to minus 1, favor the cell with relatively low value of the measure mu I on the cell. So, if mu is greater than 0, it will relatively higher value of mu I, and q is less than or equal to 1, favor the cell with the relatively lower value of the measure mu I, contribute lower values. So, these limits are best discussed by the considering the derivative of the mass exponent tau. You can take the derivative of tau with respect to q, given by d by dq of tau q is taken as minus limit delta tends to 0 mu I power q ln of mu I over sum of mu I power q times ln of delta. Let mu minimum be the minimum value of mu I in the sum. Let mu minimum be the minimum value of mu I in this sum. Then we find when this q tends to infinite, that means minus limit of delta tends to 0, sum of mu minimum power q over sum of mu minimum power q times ln of mu minimum by ln delta, where the prime on the sum indicate that only cell with mu I equal to mu minimum contributes. The sum may be rewritten as q of tau q of dq when q tends to infinity minus limit delta tends to 0 ln of mu minimum by ln delta, which tends to minus alpha maximum, minus alpha maximum. So, a similar argument in the q tends to minus infinity. If q tends to plus infinity, it is minus alpha maximum. In the similar argument in the limit q tends to minus infinity, lead the conclusion that the minimum value of alpha is given by d by dq of tau q, where q tends to minus infinity minus limit delta tends to 0 ln mu maximum by ln delta equal to minus alpha minimum, where mu maximum is the largest value of mu I, which lead to the smallest value of alpha. So, from 8 and 9, from 8 and 9, so mu minimum is directional proportional to the delta power alpha maximum. The mu maximum is directionally proportional to the delta power alpha minimum. So, we can combine the above two relations and write a general equation: mu is directional proportional to delta power alpha. Later we shall show that it is indeed the case that alpha q can be written as minus d by dq of dou q is true in general. This is true in general. That means taking the derivative of tau q with respect to q will be minus alpha q. That means minus alpha q written as minus time this value. This is true in general. Now, for q equal to 1, if q equal to 0, it will give the Hausdorff dimension, that means the fractal dimension. If q equal to 1, in the d tau by dq, you can replace 1 as an interesting value, that it gives d of dq of tau q is minus limit delta tends to 0 summation mu I ln mu I by ln delta, which is equal to limit delta tends to 0 s of delta by ln s, where this s of delta is the information entropy of the partition of the measure which we may write as S of delta can be written as summation minus time summation mu I time ln mu I, which is directionally from alpha of 1 time ln delta. That means the exponent alpha of 1 we are reaching minus d by dq of where q equal to 1. This ds is also the fractal dimension of the set onto which the measure, concentrate and describe the scaling with the box sizes delta of the entropy of the measure. Note that the partition entropy, this one at the resolution delta is given in term of the entropy S of the measure by S of delta equal to S ln delta. Now we can apply the Legendre transform of tau q and will apply the f of alpha spectrum. We have a function tau equal to tau q, which is nonlinear in q and hence its slope depends on q. So Legendre transform of tau q means another object whereby its derivative d by dq of tau can be written as minus times alpha, can be considered an independent variable instead of q itself, because the derivative we wrote here. So d by dq of tau can be written as minus alpha. It is straightforward to realize that the curve given in equation 10 can also be represented uniquely by the relation f equal to f of alpha that describe the family of tangent line at a function of slope alpha without sacrificing any of the mathematical content of the parent equation. So one can get, note that the slope of t versus q should be different at each value of q. From the curve we can draw the tangent for a given value of q and write down the equation for the resulting straight line. In general, if we denote a as the slope and the intersection f, then the equation for the line is tau can be written as minus alpha times q plus f of alpha. The function f of alpha is in fact the Legendre transform of the function tau q. Now let us see a systematic procedure to obtain the Legendre transform of the mass exponents tau q. From equation 11 we can write, that means d by dq of tau, we can write this one dt, d of tau can be written as minus alpha time dq. So rewrite this one, then d tau can be written as minus alpha time dq minus q times d of alpha plus q times d of alpha. Then the chain rule, then minus d of alpha q plus q of d alpha. Hence d of tau plus alpha q can be written as q times d of alpha. The above equation immediately reveals that we can find a new function f of alpha in term of t tau plus alpha q, where the new function f is a function of alpha. F is a function of alpha. So alpha is the mass exponent. F of alpha is written as in term of the mass exponent. F of alpha can be written as tau plus alpha q. Now what is the significant physical significance of alpha and f of alpha will discuss. The sequence of mass exponent tau q is related to the f of alpha spectrum via Legendre transformation. Recall the multifractal partition function given by the equation xi of q comma delta written as summation mu I power q, where cells are indexed by the labeling them as I equal to 1, 2, 3 etc. On the other hand, we have seen that the probability mu scaled as delta power alpha. So the distribution of the content can be subdivided into subset characterized by the alpha instead of I. Instead of I, now it is characterized by alpha. We can think of cell which scale sharing the same alpha we can now obtain the number Z alpha comma delta instead of Q comma delta, Z alpha comma delta needed to cover such a subset of the cells. Since the exponent alpha is continuum variable, alpha is the continuum variable with respect to all the Q minus infinity to plus infinity, we further consider rho of alpha times d alpha is the number of such steps from S alpha to S alpha plus d alpha. Upon transition from the discrete into continuum variable, we write the z of alpha comma tau d alpha, which is equal to rho of alpha times d alpha times delta power minus f of alpha. Then if you are taking the, hence the so called partition function can be rewritten as, that means this the partition function z of alpha, z of alpha delta times d of alpha integral rho of alpha d alpha delta power minus f of alpha times delta power alpha q, which is equal to integral rho of alpha d alpha times delta alpha q minus f of alpha. You can combine this both. The integral in equation 12 will dominated by the value of alpha, which makes the q alpha minus f of alpha smallest, provided that rho of alpha is non-zero. Thus, we replace alpha by alpha q, which is defined by the extremal condition that d by d of alpha can be written as q alpha minus f of q, which is alpha equal to which is 0. Hence, we also have, if you are taking the second derivative, the first derivative at alpha equal to alpha q, it is 0. If you are taking the second derivative, q times alpha minus f of q is greater than 0. That means, so that f dash of alpha q equal to q, f dash of alpha q is less than 0. It follows from the multifractal theory that when we have q equal to 0, then f maximum at it is equal to d, the fractal dimension d. Since tau of 0 equal to d, where d is the fractal dimension of the support of the measure, this one. So, also here f double dash of alpha q is 0, less than 0, then we can say that the multifractal spectrum f of alpha is always the concave function. So, why we are calling this as a, now if you are drawing the graph with alpha and f of alpha, it will increase and reach the maximum, then after that it will come to the lesser value. That maximum value appearing when q equal to 0, that means tau q equal to 0, this maximum appear here. Here the maximum will appear. So, after that it fall down, the curve is like the concave spectrum. Alpha with f of alpha, if you are drawing, one can get the concave spectrum. Now, you can think about this theory. Here the tau q is vary, if we are varying the different q, the mu I will vary, the mu I power q, this will vary. So, now we are taking the boxes, we are taking this curve and covering this by boxes, then in this one, if we are covering this is like this one, if this is the mu ith box, then the measure of this mu I, that means the density we are assigning as ni by n, then we are raising this probability power q, we are finding the moment, the q. For different q value and the boxes size delta, this will vary. So, this measure will gives what is the inside these boxes. So, if you are draw the multifractal spectrum, if your mass exponent at here has the fractal dimension, here it will get. So, for the same set we will get the multiple fractal dimension. Whenever the structure is more irregular, we will get the curve like the concave curve. So it will be classified by the locally by its all the subsets. So what it means, this number means that the fractal dimension of the, this is the set, the alpha, when you are taking here as alpha, then f of alpha gives the fractal dimension of the set which has the mass exponent alpha. So like that we can define the multifractal spectrum for the alpha and f of alpha. So these are all the references. So more detail we will discuss with the example in the next lectures. So what is the advantage of multifractal spectrum or multifractal measure? It does not count the number of boxes, instead of that what is inside the boxes also it carrying. Whereas if you are taking mu equal to 0, that means if the moment is 0, then mu I power q simply gives the number of boxes is required to cover the object. So this is the generalized version of the box counting dimension and as well as the Hausdorff dimension. Also by varying different q we can get the different dimensions. So with the example we will discuss in the next lecture. Thank you.